8 minutes after the sun disappears, you will witness the countdown of human civilization firsthand. Imagine standing on a street at this moment. Sunlight still bathes the ground, cell phone signals remain stable, and traffic flows as usual. But little do you know that 150 million kilometers away, the sun has vanished completely. Not in an explosion, not with a blinding flash, but simply gone without a trace. For the next 8 minutes, Earth will continue to orbit along its path by inertia, as the disappearance of light and gravity is still en route to our planet. The instant the 8th minute ends, the sky will darken without any warning. Not the gentle fade of a sunset, but as if someone had abruptly flipped off the universe's main switch. Immediately after, Earth will break free from the sun's gravitational pull, hurtling toward the depths of the Milky Way at a speed of 29.78 kilometers per second, becoming a wandering planet with no destination. You might dismiss it as a brief power outage, but what happens next will make you realize that the home we depend on for survival has already entered its final countdown. First, it's important to clarify that humanity won't perish the moment the sun disappears, but our living environment will deteriorate at an alarming rate. The first threat is temperature. Solar energy is the sole source of heat for Earth. Without the sun, the planet's surface will start a relentless cooling process. Within the first week, the global average temperature will plummet to minus 17 degrees Celsius, comparable to an Antarctic summer. Most plants will stop photosynthesizing, and crops will begin to wither. By the second month, temperatures will drop to minus 73 degrees Celsius, equivalent to the temperature during the Arctic polar night. Rivers and lakes will freeze solid, and a thick layer of ice will form on the ocean surface. However, beneath the ice, seawater will remain liquid due to geothermal heat and pressure, offering a glimmer of hope for some life to persist. A year later, the global average temperature will stabilize at minus 240 degrees Celsius, the boiling point of liquid nitrogen. Carbon dioxide in the atmosphere will start to solidify, falling to the ground like snowflakes of dry ice. At this point, the Earth's surface will no longer be habitable for any mammals. Humanity will have to take refuge in underground bunkers, relying on geothermal energy and stockpiled resources to survive. From a resource perspective, the energy supply of these underground shelters will depend on how much geothermal energy we can harness and how many fossil fuels and nuclear energy we have in reserve. Based on current energy consumption levels, all the world's nuclear power plants and fossil fuels could sustain up to 1 billion people for 100 years, but this is only an ideal scenario. In reality, a food shortage will erupt within 3 months of the sun's disappearance. Without photosynthesis, staple crops like wheat, rice, and corn will become extinct entirely, and animal husbandry will collapse due to feed shortages and extreme cold. Humanity will have to survive on pre-stored canned goods, freeze-dried food, and synthetic nutrients. Unfortunately, these reserves will only be enough to support the global population for a mere 10 years. Therefore, the true survival countdown is not hundreds of years, but just a short decade. We must find a suitable second home within these 10 years. Otherwise, human civilization will face extinction. Before we assess potential homes, we must first define a key criterion. What qualifies a planet as habitable? First and foremost, it must lie within the habitable zone of its host star. The habitable zone refers to a ring-shaped region around a star where temperatures are neither too hot nor too cold to allow liquid water to exist, a fundamental requirement for life as we know it. Second, the planet must have a moderate mass, ideally between 0.5 and 5 times that of Earth. A planet that is too small cannot maintain a thick enough atmosphere to shield against cosmic radiation or retain liquid water. A planet that is too massive will exert excessive gravitational force, making it impossible for humans to adapt. We might even be crushed under our own weight. Third, it must have a rocky surface. Gas giants like Jupiter and Saturn lack a solid surface, making them uninhabitable for human settlement. Fourth, it needs a stable magnetic field. A magnetic field protects a planet's atmosphere from being stripped away by stellar winds and shields life from the harmful effects of solar flares and cosmic rays. Finally, the star system it resides in must be stable. The host star should not be a massive star with a short lifespan. nor a red dwarf prone to frequent, intense flare eruptions. Otherwise, any life on the planet would be easily wiped out. With these criteria in mind, let's examine the most promising candidates for humanity's second home in the universe. Proxima Centauri b is the closest exoplanet to our solar system, located a mere 4.2 light-years away, or approximately 39.7 trillion kilometers. At the speed of humanity's fastest spacecraft to date, Voyager 1, the journey would take roughly 78,000 years. Yet despite this immense distance, it remains the most promising habitable candidate we have discovered so far. Proxima Centauri b orbits a red dwarf star, a star with only 12% the mass of the Sun and a mere 0.17% of its brightness. Consequently, its habitable zone is situated extremely close to the star. Proxima Centauri b has an orbital period of just 11.2 days, meaning a year on this planet lasts only 11 Earth days. Fortunately, it lies within the habitable zone, so liquid water may exist on its surface. With a mass approximately 1.3 times that of Earth, it is classified as a super-Earth and is highly likely to be a rocky planet with a solid surface. However, Proxima Centauri b also has significant drawbacks. Its host star, Proxima Centauri, is a red dwarf. While red dwarfs boast incredibly long lifespans, they are also extremely active, frequently erupting with powerful flares that release vast amounts of high-energy radiation. Because Proxima Centauri b orbits so close to its star, this radiation bathes its surface directly. Without a strong protective magnetic field, its atmosphere would likely have been stripped away long ago. Even if it does have a magnetic field, the surface radiation levels could far exceed the tolerable limits for humans. Additionally, Proxima Centauri b is most likely tidally locked. This means one side of the planet perpetually faces the star, trapped in eternal daylight, while the other side remains in perpetual darkness. The temperature along the terminator, the boundary between day and night, might be habitable, but the extreme conditions of eternal day and night would spawn harsh climate patterns, scorching heat on the day side, freezing cold on the night side, and intense storm belts in between. Nevertheless, despite these challenges, Proxima Centauri b remains one of our best hopes. Its proximity to Earth means that if humanity ever masters technologies like controlled nuclear fusion or warp drive, the travel time could be drastically reduced. Dubbed Earth's older cousin, Kepler 452b has a mass approximately 5 times that of Earth and a radius 1.6 times larger. It orbits a yellow dwarf star that is remarkably similar to our Sun, similar in mass, brightness, and lifespan. Kepler 452b has an orbital period of 385 days, nearly identical to an Earth year. It lies within its star's habitable zone, so its surface temperature is likely comparable to Earth's, making liquid water a distinct possibility. Most importantly, its host star is a stable yellow dwarf, far less prone to violent flare activity than red dwarfs. This means the radiation environment on Kepler 452b is far more favorable than on Proxima Centauri b. Kepler 452b is located roughly 1,400 light-years away, a vast distance, but still considered a neighbor within the Milky Way galaxy on a cosmic scale. However, its mass, 5 times that of Earth, implies a gravitational pull about twice as strong as Earth's. If humans were to migrate there, we would feel as if our weight had doubled. Over the long term, this would place immense strain on our bones and cardiovascular systems, requiring solutions like genetic modification or rigorous adaptation training for survival. Furthermore, due to its great distance, our current understanding of Kepler 452b is limited. We do not yet know if it has a magnetic field or what its atmospheric composition is, critical factors that determine its true habitability. Even so, based on the data we do have, Kepler 452b is one of the most Earth-like exoplanets ever discovered and a key candidate for future human migration. The TRAPPIST-1 system is a truly extraordinary stellar system. Its host star is a red dwarf with only 8% the mass of the Sun, yet it is surrounded by 7 rocky planets, 3 of which lie within the habitable zone: TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. The system is located approximately 40 light-years away, much closer than Kepler 452b. TRAPPIST-1e is the most Earth-like of the 7 planets, with a mass roughly 0.9 times that of Earth and a radius 0.92 times larger. It sits squarely in the center of the habitable zone, boasting surface temperatures that are just right for liquid water to exist. TRAPPIST-1f and 1g have masses of 1.03 and 1.3 times Earth's mass, respectively, and both also orbit within the habitable zone. The fact that a single star system offers 3 potential habitable worlds significantly increases the odds of a successful migration. However, like Proxima Centauri, TRAPPIST-1 is a red dwarf, plagued by the same issue of intense flare activity. Moreover, all 7 planets orbit extremely close to their host star. Their orbital periods range from a mere 1.5 days to just 12.4 days, making it highly probable that all of them are tidally locked, suffering from the same eternal day and night dichotomy. Additionally, because the host star is so dim, even within the habitable zone, the surface illumination is only 1% to 20% of that on Earth, equivalent to a perpetual twilight or overcast day. This would severely hinder plant photosynthesis, potentially requiring humans to rely on artificial lighting for food production. Regardless, the unparalleled advantage of having multiple habitable planets in one system makes TRAPPIST-1 a top contender for human migration. Gliese 581g is an exoplanet located in the constellation Libra, approximately 20.5 light-years from Earth. It orbits a red dwarf star and has a mass estimated to be 3 to 4 times that of Earth, with a radius 1.2 to 1.4 times larger, classifying it as a super-Earth. Gliese 581g lies within its star's habitable zone, and its surface temperature is thought to range from -12 to +10 degrees Celsius, a range that comfortably allows for liquid water. Its orbital period is 36.6 days, significantly longer than those of the TRAPPIST-1 planets. This longer orbit suggests it may not be fully tidally locked or could be in a state of tidal resonance, meaning it likely rotates, experiencing day-night cycles, a crucial factor for climate stability. However, the discovery of Gliese 581g is surrounded by controversy. Some astronomers argue that the signals initially detected may have been caused by stellar activity rather than an actual planet. But if it does exist, its habitable conditions are exceptionally promising. Its mass would result in a gravitational pull about 1.5 to 2 times that of Earth, which humans could potentially adapt to with time. Furthermore, while its host star is a red dwarf, its flare activity is relatively mild, making its radiation environment far more benign than that of Proxima Centauri b or the TRAPPIST-1 system. Currently, astronomers are using more advanced telescopes to observe Gliese 581g, hoping to confirm its existence and gather vital data about its atmosphere and magnetic field. Kepler 186f is an exoplanet in the constellation Cygnus, approximately 500 light-years from Earth. With a mass about 1.1 times that of Earth and a radius 1.17 times larger, it is extremely similar in size to our planet. It holds the distinction of being the first Earth-sized rocky planet discovered within the habitable zone of its host star. Kepler 186f orbits a red dwarf with an orbital period of 129.9 days, shorter than an Earth year, but much longer than the planets in the TRAPPIST-1 system. It resides in the outer region of the habitable zone, so its surface temperature is likely cooler than Earth's, ranging from -40 to +10 degrees Celsius. While this temperature is low, a sufficiently thick atmosphere could generate a greenhouse effect, warming the surface to a range where liquid water can exist. Its host star is a red dwarf with relatively moderate flare activity, and Kepler 186f orbits farther from its star than Proxima Centauri b does, resulting in lower surface radiation exposure. However, the star's low brightness means surface illumination is only about 32% of Earth's, similar to a cloudy day. This would reduce the efficiency of plant photosynthesis, potentially necessitating the development of specially engineered crops or reliance on artificial light for agriculture. On the plus side, Kepler 186 fs mass and radius are nearly identical to Earth's, so its gravity should be very similar. This would mean minimal adaptation for human settlers, a significant advantage. Having surveyed these potential habitable planets, a more pressing question emerges. How can we actually get there? Currently, humanity's fastest spacecraft is NASA's Parker Solar Probe, which can reach speeds of up to 200 kilometers per second. Even at this blistering pace, the journey to Proxima Centauri b, the closest candidate, would take roughly 6,300 years. This is far beyond the span of a human lifetime, and even the duration of human civilization itself. Therefore, to achieve interstellar migration, we must overcome our current technological limitations. First, we need to revolutionize our propulsion systems. Controlled nuclear fusion is the most promising technology on the horizon. It could provide a nearly limitless supply of clean energy, propelling spacecraft to speeds of 1% to 10% the speed of light. At 10% the speed of light, the trip to Proxima Centauri b would take just 42 years, and reaching the TRAPPIST, one system would take 400 years, timescales that are manageable within the context of human history. Even more advanced concepts include warp drive and wormhole travel. Warp drive works by warping space-time, allowing a spacecraft to move within a space-time bubble at speeds exceeding that of light. Wormholes, on the other hand, are hypothetical shortcuts connecting distant points in the universe. However, these technologies currently exist only in theory, requiring the resolution of immense challenges related to energy requirements and space-time stability. Second, we need to construct large-scale interstellar arcs capable of sustaining thousands of people during long-duration space travel. These spacecraft would need to feature self-contained ecosystems that recycle water, air, and food, along with robust shielding to protect against cosmic radiation and asteroid impacts. Finally, we need to solve the problem of human longevity. Even if we can achieve 10% the speed of light, reaching more distant habitable planets would still take centuries. This would require breakthroughs in technologies like genetic modification, cryogenic hibernation, or even consciousness uploading, enabling humans to survive the lengthy voyage through space. After the Sun vanishes and Earth becomes a wandering planet, we will be treated to cosmic spectacles never before witnessed by humankind. First, the sky will plunge into profound darkness, but the stars will shine with unparalleled brilliance. Freed from the sun's glare, we will be able to see the Milky Way in its full glory, a dazzling band of light stretching across the heavens, far brighter than the faint streak we see today. Second, we will observe the proper motion of stars. As Earth hurtles through space at 29.78 kilometers per second, the stars around us will slowly shift their positions in the sky, much like how trees appear to move when viewed from a speeding train. Currently, due to Earth's relatively slow orbital speed around the Sun, it takes centuries to detect noticeable proper motion. But on a wandering Earth, this process will accelerate dramatically. Third, we may encounter other star systems. As Earth drifts through the Milky Way, there is a small chance it could drift within the gravitational influence of another star and be captured as one of its planets. If we are fortunate, this new host star could be a stable yellow dwarf, and Earth could settle into its habitable zone. In that case, humanity might not need to migrate at all and could continue to survive right here on Earth. However, this probability is extremely low. The distances between stars are so vast that the chance of Earth encountering another star is akin to two ships meeting in the middle of an endless ocean. Fourth, we will witness more supernova explosions and gamma-ray bursts. These are the most violent explosions in the universe, releasing staggering amounts of energy and light. Although they are far away and pose no direct threat to Earth, they will appear as brief, brilliant points of light in the sky, nature's most spectacular fireworks display. When we discuss the scenario of the sun's disappearance and human migration, we are compelled to ponder a deeper question: what is the meaning of human civilization? Earth is our home, but in the vastness of the universe, it is merely a tiny blue speck. The sun is just one of hundreds of billions of stars in the Milky Way, And the Milky Way itself is only one of hundreds of billions of galaxies in the observable universe. On a cosmic scale, human civilization is like a grain of sand on a beach, ephemeral and insignificant. Yet it is precisely this insignificance that makes our existence so precious. We are the only known intelligent life in the universe. We possess the ability to contemplate the cosmos, to explore the unknown, and to create civilization, art, science, and technology, all unique achievements in the universe. The disappearance of the Sun and Earth's wandering, while a catastrophic scenario, also serve as a wake-up call. Humanity cannot rely on Earth forever. We must step out of our comfort zone and venture into the depths of space. Only by doing so can human civilization endure in the long run. At the same time, this topic underscores the loneliness of the universe. Despite our extensive searches, we have yet to find any trace of other intelligent life. Humanity may be truly alone. This loneliness teaches us to cherish one another and to value all that we have. It also strengthens our resolve to explore the cosmos. We hope to find other habitable planets, to discover other intelligent beings, and to no longer be alone in the universe. This curiosity about the unknown and this drive for survival are the very forces that propel human civilization forward. Although the disappearance of the Sun is a hypothetical disaster, it serves as a stark reminder that Earth is not eternal, and neither is human civilization. We must face this reality and plan for the future now. Planets like Proxima Centauri b, Kepler 452b, and the worlds of the TRAPPIST-1 system are beacons of hope for humanity's future. While we lack the capability to reach them today, with the continuous advancement of science and technology, we firmly believe that one day, humanity will build powerful interstellar spacecraft, embark on the journey of migration, leave Earth, and travel to distant planets. This is not just about survival. It is about the continuation and evolution of human civilization. The universe is vast and full of the unknown. It holds both perils and promises, both loneliness and miracles. Humanity's future is not on Earth. It lies among the stars and seas. Each and every one of us is an explorer of the cosmos, a custodian of civilization. Let us strive together to keep exploring, to keep progressing, and to create new possibilities for humanity's future. Finally, I would like to ask all of you, which planet do you think humanity is most likely to migrate to? What are your thoughts on interstellar migration? Please leave a comment below and join the discussion. If you enjoyed this video, don't forget to like, subscribe, and share. We'll see you next time.